Today we're going to do 4.7 change of basis. When a basis B is chosen from an n-dimensional vector space V, the associated coordinate mapping onto Rn provides a coordinate system for V. Each x and v is identified uniquely by its B coordinate vector. So the B coordinate vector of this is 3, 1. So 3, 1. And the C coordinate vector of this one would be 6, 4. So 6, 4. So let's look at example 1. Consider two bases, B1 and B2, and C1 and C2 for the vector space V such that B1 equals 4C1 plus C2, and B2 equals negative 6C1 plus C2. Suppose X equals 3B1 plus B2. Suppose the B coordinate vector of X is 3, 1. Find the C coordinate vector of X1. So the first thing we need to do, so there's two ways to do this. So I want to find the C coordinate vector of X, and we know that this equals 3B1 plus B2 of C. And this would equal 3B1 plus the coordinate vector of B. So now we're going to write this as a matrix equation. And we know that B1 and B2 are 4, 1 and negative 6, 1 respectively. So B1 would be 4, 1, B2 would be negative 6, 1. Those are the coefficients of our C vectors. And then when I multiply this, I would get 6, 4. So if you look at the previous page, we just considered those two bases, B1, base B, and base C, to get this. The other way that you could do this is have X equals 3 times 4 C1 plus C2 plus negative 6 C1 plus C2. And this would be 12 C1 plus 3 C2 minus 6 C1 plus C2. This would then be 6 C1 plus 4 C2. And your coefficients would be 6, 4. Same thing. So that's a little faster how to do it, but this is the correct notation using matrices. So let's look at theorem 15. Theorem 15. Let B be the set of vectors B1 all the way to Bn, and C be the set of vectors C1 all the way to Cn, be the basis of vector space V. Then there's a unique n by n matrix P such that the change of coordinates goes from B to C. So this is my C coordinate vector for X, and this is my change of coordinates go from B to C. The columns of P from B to C are the C coordinate vectors of the vectors in basis B. That is, when P maps from B to C, it would equal all the columns. The matrix P mapped from B to C is called the change of coordinate matrix from B to C. The columns of P that map from B to C are linearly independent since it is a square, and it must be by the invertible matrix theorem. So the inverse is of my C coordinate vector is the B coordinate vector. If B and C is in the standard basis, so if B and epsilon are in the standard basis in Rn, then B epsilon, so there should be an epsilon right there, and it's missing, so make sure you put that in. So my P vector from B to epsilon would be P times B1, B2 all the way to Bn. Let's look at example 2. Consider two bases B and C for the vector space V such that B1 equals 4C1 plus C2, B2 equals negative 6C1 plus C2. Suppose that X equals 3B1 plus B2. Find the change of coordinate matrix from C to B. So we're going to find our change of coordinate matrix from C to B. And this would be the same thing as P inverse from B to C. So B1 would be 4, 1. B2 would be negative 6, 1. And it's the same as the inverse. So the inverse would be 1/10 times 1, negative 1, 6, 4, because we switch these and take the negative of the other diagonal. And my answer would be 1/10, negative 1/10, 3/5, 2/5. And that's all using the previous theorem. Let's look at example 3. Let B1 be negative 9, 1, B2 be negative 5, negative 1, C1 be 1, negative 4, and C2 be 3, negative 5. And consider the basis for R2 given that B is B1, B2, and C is C1, C2. Find the change of coordinates matrix from, that should be B to C, not C to B. So let's go ahead and fix that. So we need to find so we're going to let my B coordinate vector of C equal this, and the second one be y1, y2. So then we would have C1, C2 times x1, x2 equal B1, and we would have C1, C2 times y1, y2 equal B2. So what we can do is take in this matrix C1, C2, our partition matrix B1, B2, and go ahead and row reduce this until we get our identity matrix on this side, and that will give us our change of coordinate matrix from B to C. So we have 1, -4, 3, -5, -1, -5, 1, -1. First, I can go ahead and take 4 row 1 plus row 2. And get 0, 7, -35, -21. And then I can take -3 row 2 plus row 1 and 1/7 of row 2 to get my so first take 1/7 of row 2 and then -3 times row 2 plus row 1. And you would get 6, 4, and then -5, -3. Therefore, my change of coordinates matrix from B to C, which was B1C, B2C, would equal 6, -5, 4, -3. And keep in mind, note that this partition matrix here equals the identity matrix and then the change of coordinate matrix. Okay, so when you're reducing it, you should get the identity matrix, and then this would be your change of coordinate matrix. Let's look at the last example. Let B1, B2, B1 be 1, -3, B2 be -2, 4, and C1 be -7, 9, C2 be -5, 7. And consider the basis for R2, given that B is B1, B2, and C is C1, C2. Find the following: the change of coordinates matrix from C to B, and the change of coordinate matrix from B to C. So let's go ahead and do A first. So from C to B. So to set this up, you'd have B1, B2, C1, C2. This would equal 1, -3, -2, 4. And -7, 9, -5, 7. First, I can take 3 times row 1 and add it to row 2. And I'd get 0, -2, -12, -8. And then I can take 1/2 of row 2, -1/2 of row 2 to get 1 here, and then negative row 2 and add it to row 1. So I'm doing 2 steps. First, I'm going to take -1/2 of row 2, and then I'm going to take negative row 2 and add it to row 1. So my change of coordinate matrix from C to B would be 5, 6, 3, 4. Okay, and B, to find it from B to C, this would just be the inverse of C to B. So I would be finding 5, 6, 3, 4 inverse. This would be 1/2 times 4, -6 negative 3, 5. So I would have 2, negative 3 halves, 5 halves.